the Doppler effect. Here's how it works. All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. We hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because the sound waves are now spread out by the car.
Light waves show a similar shift. If a source of light, like a star or a galaxy, is moving toward us, the light waves are bunched together, and we see the light with a slight bluish tint. If the star or galaxy is moving away from us, the waves are stretched out, and we see a reddish shift in the color. Because all galaxies show a red shift in the color of their light, this is evidence that they're moving away from one another. So the red shift is evidence that our universe is expanding.
Applications of Doppler effect. The illustration shown here will help you understand the Doppler effect. I'm sure you would have heard an ambulance speeding past you. That is, the pitch of the siren increases as the ambulance approaches you, and the pitch decreases when the ambulance moves away from you. There is a similar apparent change in the pitch of the sound heard when the source of sound is at rest and the listener moves towards or away from the source. The change in pitch is due to a shift in the frequency of the sound waves. Based on these observations, an Australian physicist and mathematician J.C. Doppler proposed the Doppler effect in 1842. According to the Doppler effect, the apparent change in wavelength of sound or light is due to the motion of the source, observer, or both. Doppler effect is observed in light also. Suppose a star recedes from Earth, then the frequency of the light emitted by the star decreases or wavelength increases. Thus, the spectral lines are shifted towards the red end of the spectrum. This is called redshift. Similarly, when a star moves towards the Earth, the spectral lines shift towards the blue end of the spectrum. Applications of Doppler effect. To find the velocity of a speeding car. Let us see how a traffic police catches speeding motorists. Short waves emitted from an observation center are directed towards the speeding vehicle. These waves are reflected by the car to the observation center. By calculating the shift in the wavelength, the velocity of the speeding car can be determined. To determine the depth of oceans, we can apply the Doppler's effect for estimating the depth of the oceans. For this, we make use of sonar. A transmitter from a ship transmits sound waves towards the ocean floor. These waves are then reflected by the ocean floor and are received by the receiver. Note the time taken by the waves to come back to the source. Now we can estimate the depth of the ocean by using the formula T is equal to V into T by 2, where V is the velocity of sound waves and T is the time taken. To calculate the speed of astronomical bodies. The Doppler effect of light can be used to measure the speed of stars and galaxies. The spectrum of light coming from the planets and stars are photographed over a long period. By observing the Doppler shift, one can conclude whether they are moving towards or away from the Earth. To study Saturn's rings. Concentric rings surround the planet Saturn. These rings reflect light and are not self-luminous. The Doppler shift of light reveals that the rings are not continuous, but they consist of many particles.
It's a simple experiment that should show what happens when shock waves are contained or released. All he needs now is 2 model rooms.
Now, why is the conventional wisdom that the explosion that did not kill Hitler in the room with windows would have killed him in the bunker? I'm hoping to tease out the reasons for that thinking with this visualization. Before me, the 4 walls of the bunker. I'm going to drop this little weight into the center. Let's see what happens. Let's look at the high speed.
The idea is that the ripples or waves of water behave much like a percussive blast through air.
Awesome. My visualization of waves in a closed room worked just the way I hoped. You can see the waves traveling out from the weight that I dropped, hitting the walls, and then bouncing back. They've got nowhere to go.
Now, to see if throwing open a few windows really makes much of a difference.
All right, so this is my situation room. Each of these spaces is an open window. Here is my bomb. Let's see what happens. Perfect.
The high speed confirms what Adam suspected.
That is so cool.
Give a wave half a chance to escape, and it takes it.
So what can we surmise from this? We can clearly see in the closed room the waves are contained. They do not escape. And we can see in the open room with windows that the waves totally get out.
So it looks like there's some science to back up the myth.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce 2 booms. They just reach us so quickly in succession that we can't distinguish the 2. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight.